My name is Dane Bennington, and this is the philosophy of robotics as applied to FRC. I tried really hard to find a good framing device for this talk. In the end, this is going to be a talk about automation, but there's a little bit of history and a little bit of technology built into it, so lots of fun. A little bit about me. I'm a FIRST alum. I've been doing FIRST for 17 years. Started in FLL, did FRC as a high schooler, and then I've been a mentor for 11 years, both for Team 1425 and 4991. I have a master's degree in electrical and computer engineering from Carnegie Mellon. I also have a bachelor's in EE from Rose-Hulman. I've worked at NASA and at NREC. I used to work at Argo, and now I'm at Stack AV working on autonomous trucks. I'm mostly a hardware guy, but I'm sort of a jack of all trades, master of, exactly one. So, quick disclaimer, this is meant to be sort of like a crash course into the theory of robotics that you'd run into at a college course, but delivered in, well, it would have been an hour. Now it's more like 45 minutes if I get that lucky, and geared heavily toward FRC. I get badly sidetracked. I'm going to try to keep that to a minimum. And some of this isn't robotics. This is just stuff that has been bouncing around in my head. With that out of the way. When you're playing a FIRST game, your robot is really the game partner that's on the field. Ideally, the driver, the co-pilot, the human player, and the robot all have to be working together as a unit. The robot is a member of the team and is thus really designed to be something that is supposed to correct for any deficiencies of the team. And since you have the ability to build it, you're the one who gets to choose exactly what deficiencies it helps with. A good robot will excel where you're weak and rely on the team for things that it's really hard to build a robot to do. It also has the inherent advantage that it's the only thing that's allowed on the field. I'm sure that if any of us were to go out onto a field and go handle game pieces, we'd outperform the crap out of the versus other robots, but that's not allowed. Down below, that's my high school senior year robot doing an autonomous mode with an amazing, totally planned bounce score. That's, you'd really love a robot that...
Your calculations for that must have been a bear.
I mean, in 2007, it was nuts. So let's talk a little bit about robotic control paradigms. And this is from a theoretical standpoint. This is a great video from the DARPA Robotics Challenge. And yes, even robotics engineers find this hard. Bonk. Yeah, the tasks here were many and varied. You had to drive a car, you had to open a door, you had to turn a valve, you had to climb stairs. It wasn't pretty. All right, so what do I mean when I say a paradigm? Well, a paradigm is the idea that it's a way that you structure a robot's code. A robot is supposed to perform an action that allows it to achieve a goal. The hard part is figuring out what actions it should take. That can be very simple, such as extend your arm, or it could be very complicated. Score a point at the other end of the field. Historically, there have been various attempts at creating robotic architectures that create sort of intelligent behavior without explicitly programming it in. And that's ultimately the goal in a lot of early robotics. How do you program something that, quote unquote, thinks for itself? This is somewhat applicable to FIRST robotics. No one's going to build a fully autonomous FIRST robot, but bear with me. The history gets interesting. So your sort of 0th level is remote control. It's super simple. Most of you could program this in about 10 minutes. It's very flexible. It's only dependent upon you hitting a button. But it really requires that your drivers are extremely good and you spend a lot of time practicing. And then, of course, once you practice and get it down pat, you go out onto the field and you try to do it during competition and you fail miserably trying to line up a goal that's 30 feet away and has an error of about an inch. So this is kind of not robotics. This is fancy RC car. Again, this is where most people start, and that's fine, but I think we can do better. So let's get into the earliest of control paradigms, that of the reactive paradigm. This is sense-act, that's the way to think about it. It's pretty simple, it's extremely fast, and it's useful in very specific cases, but as soon as you get outside of those simple cases, it starts failing. This is things like, if a touch sensor is detected, turn the robot. Or if the limit is reached, stop driving the elevator. Or if there's something in my claw, grab it. This is usually pretty useful. And in very early robotics, this was very popular. In the late 1940s, W. Gray Walter created these tortoises, he called them. They were extremely simple. They didn't even have a computer on them. They just had a pair of vacuum tubes. And it was programmed, I say programmed, I mean hardwired. It would drive toward dim light sources. It would drive away from bright light sources. And if it was bumped, it would turn around. This is actually the forerunner to sort of the first generation Roombas, if anyone's old enough to remember those. And really, that's all it needed to do. It could just drive around, and if it hit a wall, it would turn around. And that's all that was necessary. And then it also had the ability to go seek a charging base, which was quite fancy. But the idea was in the late 1940s that very simple robotics and very simple animals and insects were sort of collections of these reactive control paradigms. Sort of like, if something touches you, move away from it. If you see food, go toward it. If you see a potential mate, go toward that. And if you just stack enough of these together, you get intelligent robotics. They called this cybernetics. I don't know why they went back to biologically inspired robots. Cybernetics is way the hell cooler, but is what it is. So at the other end of the spectrum, we have the deliberative paradigm. This is also known as the hierarchical paradigm. This is known as sense, perceive, plan, act, or sense, plan, act if you're a little older. It's flexible in the sense that you don't specifically have to tell the robot what to do. It's fast as compared to driving it yourself. It's slow as compared to reactive. But it's extremely complex and extremely finicky. So deliberative is more like what you would think about when you think about how does a robot do a thing. A very common example is a key is on the table. Go get the key. So first the robot says, well, what's a key? Well, I know what a key is. Good. That's something that has been programmed into me. What's a table? I know what a table is. Can I sense the key? Yes, it is on the table. Will the key move? No. The thing I know about keys is they don't move unless they're moved. Now I need to plan a way to drive toward the table and reach out and grab the key. And it will figure all this out, it'll think about it really hard, and then it will do it. As you can imagine, it's really, really hard to do that. I mean, just the physics modeling of figuring out if I reach out and is my arm going to whack into the table, that alone is an extremely difficult problem. And this was really sort of pioneered in the late 60s, back when the computers, they were okay, but you're not going to do crazy things with them. So we had Shaky the robot. This was the first robot that really sort of exemplified this. And Shaky was kind of interesting. You could take a really high-level command, like go into the next room and turn off the lights. And it would figure out what steps were necessary in order for that to happen. It could plan how it was going to get from here to there. It could detect all the things that are in its way. It could avoid them. And it could go and do these things. And it's considered one of the most important robots in the field of robotics because of that. But its environment was extremely simple and extremely engineered. You couldn't just put it outside and say, go find an arbitrary light switch and turn it off. It had to know everything about its environment in order to make it work. So you put these two together, and this is a pretty common thing. You get the hybrid paradigm. The idea is that you have sort of these low-level reactive things that allow it to act faster than sitting and thinking about it. But at the same time, you have the ability to sort of sit and think about what you want to do. So it's sort of like if you are walking around the kitchen looking for your keys, at the same time you could be planning your drive to work. You have the low-level stuff that sort of thinks about what you want to do, or that take care of the things that you have to do, while you have the high-level stuff that thinks about what you want to do. And there are examples of this. I'm going to sort of speed through this in this case. This was very popular in the late to mid-90s. There's also another paradigm out there called the subsumption paradigm. And that was the idea that, well, reactive really had a good idea there. Obviously, we can get some pretty complex behaviors out of robots just by stacking together all these reactive elements. But really sort of stacking a bunch of them and expecting a complex behavior out of it was asking a little too much. So what if we sort of made a low-level controller that said, I'm going to do nothing but make sure I don't run into anything. That's all I do. And then you do a higher level controller on top of that that says, I want to wander around. But it still defers to that first level controller that says, I don't want to run into anything. The nice thing about this is it's pretty modular. You can sort of stack more and more complex behaviors on top of one another. But at the end of the day, in order to do really complex behaviors, you really need a planner. And just sort of stacking simple controllers on top of one another didn't really get you very far. This was popularized in 1985 by Rodney Brooks of MIT. And I mean, you'd have to ask him, but generally speaking, the consensus is between that and reactive paradigms, it really set the field back by about 20 years. So to recap, early robotics, mostly reactive. They were very simple. They sort of mimicked animals and insects. Later, roboticists said, well, let's go top down. Let's think about defining all of the entire world in terms of, in this case, it was known as symbolic AI. Sort of, let's define what the entire world looks like to the robot and let the robot think and really, really think about what it wants to do. But it turns out that's really hard to do. In essence, what has happened is that big computing and machine learning has come along and really saved deliberative. One of the base problems of deliberative programming one of the big problems that you run against symbolic AI, which was very popular prior to big machine learning, was that you were continuously trying to define these concepts in terms of other concepts, and eventually you need something solid that the robot can come up against. And any of us can, for instance, define what a table is, or define what a chair is, or define any of these objects, except for some corner case. A table is a flat surface with 4 legs, except when it's not. And people are very good at saying, well, okay, but that's still generally a table. You use it like a table. But a robot says, but you didn't tell me that's a table. So this is some of the big problems that we're coming across. And this is how people in the past 50-ish years tried to solve it. So let's talk about what these individual steps really mean. And before we move on, I do want to pause briefly for questions and also to recognize how close that man came to being decapitated. Nothing? All right.
Yeah. Just one thing about the reactive control. So I think you're using the reactive control in a slightly different way than I would think of reactive control as closed loop control, because I think at the very bottom of the thing, you're still doing in some ways closed loop control on some of your motors and stuff. Is that? Are you saying there are other algorithms? I mean, even states-based control in a way is a feedback control. It's a little more intelligent feed forward in some ways, right?
I'd agree.
And so you're still doing reactive control even with all these other ones in that sense, but maybe not in the other sense that you mean, which I'm not sure I completely got.
You run into a lot of the sort of nomenclature issues, particularly in this sort of thing where everything sort of runs together. I had a professor once who was talking to me about adaptive control. I was like, what is an adaptive control? Well, technically a PID controller adapts. But yeah. So I think you're correct. I think the way to think about it is that usually a closed loop controller is used to make a robot act more like a model. Whereas these are trying to create particular behaviors by saying, based on the model of my world, I think I want to do this. So it's a slightly higher level. So
yeah, so if you look at the industrial way that the industry looks at controls, there are levels, right?
Absolutely.
The bottom level is the control the thing level.
Yep.
And the levels above that are
Yeah.
And so the bottom level is still the bottom level.
And you could say in a reactive control, for instance, when you poke this, or when this sensor is touched or it goes off, set my velocity control loop target to X. And that would still technically be a reactive paradigm with a closed loop controller on it.
I just wanted to make sure I understood.
Oh, absolutely.
Thank you.
Oh, absolutely. So what is sensing? Well, that's kind of a trite question, but let's be specific about it. Technically speaking, a sensor is a device that creates a signal in response to